Hey guys, hope everybody's doing okay. This is Mr. Krowski. What we're going to do today is take a look at something called Photoelectron Spectroscopy. This is a relatively new addition to the AP Chemistry curriculum. I could have mentioned it and brought it up in Honors Chem, but I decided to save it for this course because it's a little bit more in-depth. So this really builds on what we've looked at so far in terms of the history of the atom. So if you think about that history of the atom, from Dalton's first atomic theory, and then we had J.J. Thomson with his cathode ray tubes, right? He did an experiment and looked at data and then modified the model of the atom. And then Ernest Rutherford did an experiment, the gold foil experiment, and he collected data, right? And therefore the model of the atom had to change. And then, after Rutherford, we had Niels Bohr. So Niels Bohr looked at his data with the light and the the atomic emission spectra, and again we modified the atom to look at how our electrons kind of located in terms of energy levels. And now we kind of talked about the quantum mechanical model, right, where we had the order of filling 1s2, 2s2, 2p6, and so on. But we never really talked about why it is that way. So this is why it is that way. So this is the data that is going along with that to kind of show us that that's what the model of the atom is right now. So you can kind of see the progression here. Dalton, Thomson, this plum pudding model, Rutherford with his dense nucleus of a positive charge with the electrons just around it, and then we had Bohr where we had energy levels. Here's our emission spectra for probably hydrogen. So what's this data to lead us to the quantum mechanical model? Okay, so we can have that order of filling and have things called orbitals in these various shapes. Well, it's PES, or photoelectron spectroscopy. It's really easy on the surface here to kind of understand it and see why things are like they are. Of course, it can get way more complicated, but we're going to try to simplify as much as we can here. So here's your PES instrument right here. And what you end up having is you have a source of photons, okay? So like an energy source, right? And it generates UV and X-rays, and it shoots those at some sample of atoms, okay? This type of radiation has enough energy to expel not only the valence electrons, but in addition to those, your core electrons. Okay, it's called the photoelectric effect, and it was mentioned earlier in this unit, and it's in some other videos on my channel here. The kinetic energy of the ejected electron is measured. Okay, so the electrons are ejected, okay, from the sample, and they go into the analyzer here, and how much energy they have is recorded. Okay, that's called the binding energy. So what happens then is the PES instrument, okay, this whole instrument here, gives you a reading, like a spectrum, and it shows you all the different binding energies of these electrons. So it would make sense, and we'll get into this more throughout the unit, it would make sense that the electrons that are closest to the nucleus, it's going to take more energy to have those, to get those to be expelled from the sample, right, than the valence electrons. The valence electrons are easier to remove. They're further away. There's less nuclear charge holding them in, right? And there's more shielding. There's just more distance between the nucleus and those valence electrons. So it's easier to remove them. So that's going to be a big important key here when we look at these spectra. The higher the binding energy, the larger that is, the closer to the nucleus that electron was located. Okay, because again, closer to the nucleus, harder to remove because of nuclear charge and shielding and just distance from the nucleus, energy levels in general. Okay, so here is our sample down here. Okay, we have our X-ray or UV source right here, and we have our analyzer. And try to pay attention to the energy coming out, hitting some electrons here, and them going into the analyzer, and what happens over here with the spectra, like the readout. All right, let's watch. Okay, so we had some, that one missed. Okay, so not all the electrons go into the analyzer. but a lot of them do. Okay, so we're still firing our energy here at our sample. Another one missed just there. Okay, another one in. Okay, I think that is the end of that animation. Okay, so let's look at what we have here. We have 2 peaks. Okay, now you can see this is, what is element number 3? This is lithium, okay? Lithium has 3 protons. That's what's showing us here. The nucleus is a +3. Now we have 3 electrons, right? These are not ions. So this is our lithium atom. And when the energy source came in and was able to remove those electrons, the electrons absorbed some energy and they were removed. They hit that kinetic energy analyzer. We ended up with 2 peaks here. So we have a peak with a binding energy, ionization energy, another way to say that, 6.26, another one with 0.52. All right, one peak is higher than the other one is. So it's about twice as high. So this 6.26 has to represent the electrons in the level that's closest to the nucleus. So let's pick one of these. You can see that the level closest to the nucleus right here, we have 2 electrons in it. This peak here, with a lower binding energy, it's easier to remove that electron. It has to be from the second level. Okay, second level, easier to remove, and the peak is a little bit shorter. So what does this really mean here? This means, as we blow it up, we have our inner shell electrons here for that first peak. Okay, our outer shell electrons here for the second peak. So we have 2 sets of peaks here, right? We have our set here, which is just 1, and our set here, right? So this tells us we have 2 different energy levels because that binding energy is so far away. It also tells us the relative amount of electrons we have as well. Okay, so I already went over some of these questions. The electrons that require the 6.26 are the inner shell electrons. Oops. And the peak here, okay, is going to be the outer shell electrons. And if you notice, that first level has 2 electrons. So this is like representing the first level of electrons, 1s2, right? And here's our second level of electrons. That would be 2s1. All right, let's take a look at another one. I kind of jumped the gun there. Let's do boron. So let's fire up our machine here, and let's see what happens. Some things to take note of here. Boron has 5 protons, hence the nucleus of +5. It also has 5 electrons. Still only in 2 energy levels, though. The 1s and the 2s. And the 2p. Okay, so the first level has 1s, and the second level has 2s and 2p. Let's see how that shows up here. Okay, it's still going. You can see what we're forming here. We're still getting 2 sets of peaks, right? But we're getting, in this set over here on the right, we're getting 2 peaks in that set. Let's see what that could possibly mean. I think we're about done here. Okay. So, this is lithium. Okay, that's the one we just did. Lithium was 1s2, 2s1. Okay, so we had 2 energy levels, so 2 sets of peaks, and then we had 2 electrons in the first level, right? So that peak height was double of this, which only had 1. Now we have boron. Okay, if you were to write out boron's electron configuration, it'd be 1s2, 2s2, 2p1. Okay, so let's see. Didn't blow up any bigger here. So our first electrons, binding energy of 19.3, all right? So that's going to be our electrons in the first level. We only have 2 of them there, 1s2. Now look at this next peak. We know it's our second level, right? This is our second level. The next electrons that we would fill would be our 2s electrons. And I just said it would be 2s2. Okay, so look at that. peak height should be the same because we have the same number of electrons, right? So there's 1s2, 2 electrons, 2s2, 2 electrons. Peak height's the same. Our last one here should be 2p1. 1 electron versus 2, our peak height should be about half, and it is, okay? So they looked at these readouts and said, okay, we have big differences in binding energy. That has to tell us our energy levels. And then within an energy level, like right here, we have multiple peaks within an energy level. What does that tell us then? Well, that tells us within an energy level, we're going to have like sublevels, and that's where we get the S, P, D, and F subshells from, right? Just nice how this kind of all makes sense here, and you could see some data here that like backs up why we went through that whole quantum mechanical model and had the order filling like we do. So here's that comparison between the two of them again, lithium and boron. So some redundant questions here. Which peaks represent removing the electrons from the first level? That would be these peaks here. This is interesting. This is PES, these PES readouts. You probably already noticed. Where is 0 located? Well, 0 is located here. 0 is always going to be as far to the right as possible. All right. So we're working from left to right, inner shell electrons to outer shell electrons. The easiest to remove are those outer shells. So they're going to be closer to a binding energy or ionization energy of 0. The left-hand side of your x-axis there, this bottom part is just going to be, as big of a number as you really want, like whatever the readout has. Like here we have 19.3, here we had 6.26. And that leads us to the next question here. Apparently the second question, number 1. Why do lithium and boron have different binding energies for the first energy level electrons? So that's a really important point here. The binding energy for lithium for the 1s2, for those electrons, it's 6.26 megajoules per mole, because we're moving a mole of these electrons, right? Look at boron, 19.3. So much bigger. Why? They're still just the first level. It's still just 1s2. Well, here's some of this detail you need to understand. Lithium has how many protons in it? Lithium has 3 protons. Okay? Nuclear charge of lithium is 3. It's a positive 3 charge pulling in on those electrons that you have in lithium. Now look at boron. Boron is number 5. It has 5 protons. Okay? So what's stronger here? The nuclear charge of boron is stronger. 5 protons pulling in on the electrons versus 3 protons pulling in on the electrons. Talking about in honors, talking about it now a little bit, the number of protons, that's like the strength of that nucleus. That's telling you how strong of a pull does that have or enforce, like on those outer shell electrons, or just electrons in general, right? So lithium only has 3 protons pulling in, and boron has 5, so it'd be harder to remove electrons from boron in general because of that. Okay, last question. What do boron's peaks at 1.36 and 0.80 tell us? I already went over that. That is, these represent your second level electrons, and since there are 2 peaks within that second level, it represents our subshell. All right, so 2s2, 2p1, good to go. So, to recap here, the data that supports our subshell theory is what we just went over. So we have peaks on our readout that give us like different chunks, right? So we have the first energy level peaks, the second energy level peaks, and the third energy level peaks. The y-axis is the relative number of electrons. So the scale here is a little weird sometimes, but it's how many electrons you have per peak, basically, right? That height tells us how many we have. There's no like number here. We just have to look at the relative height of those, compare one height to another height. All right. This is interesting. I don't know what element this is off the top of my head here, but we have 1s2 for whatever element this is. And then we have 2s2. Okay. Those peaks should be the same height they are. Now look at this next peak. It is how many times bigger than the first peak? Well, that first peak took up 2 lines. This one takes up 3, 4, 5, 6 lines. So if it's 3 times higher than this peak, it should have 3 times the number of electrons. So this would be our 2p6. All right. Here we have third energy level, 3s2. 2, because it's the same peak height. And then look at this. This peak height is half of this, so it should be half the number of electrons. That would be 3p1. And that gives us 1s2, 2s2, 2p6, 3s2, 3p1. This is aluminum. That's the PES for aluminum. Okay, so again, PES measurements give us data to support the idea of subshells, which are electrons in the same energy level but slightly different energies. And we can see that here. I just went over that. Okay, just going over this again here. This is aluminum again, right? So we have our different subshells, and you can see the different ionization energies for every electron. Okay, so for aluminum, you can see it's not filled in all the way. You have 580 megajoules per mole to remove the first electron, 1815 to get the second electron, and so on and so forth here. Okay, obviously, as you remove more electrons, it's going to be more difficult to remove them because that attraction increases more and more. As you're removing electrons, you're getting closer to the nucleus as you're removing those, because you always remove the outer electrons first. Okay, so if you look at the readout up here, it would definitely be easier to remove that 3p1 electron first compared to the 1s2 electron from aluminum, right? So you always work from the outside to the inside in terms of removing electrons. Let's analyze some of these. You could look at your nucleus here. You could draw it in if you want to. You could assume it's there. And then again, as you move from left to right, you go from inner to outer level there. So we have our 1s2, 2s2, and then 1, 2, 3, 4, 5, 6. That would be 2p6. Okay, 1s2, 2s2, 2p6. This is neon. All right, so you can go through and answer that one. That's an easy one. Neon is going to be the answer to that question there. Next one, identify the element and its electron configuration. So here are our choices: boron, aluminum, silicon, or sodium. So take a second and pause the video so you can figure this one out. We're going to go through, and this will be our 1s2, 2s2, 2p6, 3s2, and 3p1. All right. So that is going to be aluminum. Its electron configuration we already have there. So put all those together and you have aluminum. Okay, that was our example on a previous slide as well. It doesn't always look this nice and neat and orderly. All right, so this is what an actual readout would look like. So there's a lot of like background stuff you got to work your way through. This goes along with any sort of readout you would get from real machinery. If you take some college chemistry labs and you use like an NMR or IR, I've used some of those. You get a lot of noise you got to work your way through. So you can see that there's the peaks here that matter, and there are some peaks that, like here, looks like a little bit of noise. So you have to kind of differentiate that. What you'll have to do here in this class and in AP Chem is you'll analyze these cleaned up versions, which is really nice. You don't have to worry about what's noise and what's not noise because you don't know how the machine works that in depth or anything. Okay, so there are a couple practice problems. We're going to go through these together, and then you're going to try a bunch on your own. So, on the PES spectrum of chlorine, label the sublevel of each peak and draw what the spectrum would be for sulfur. All right, so let's take a look at that. So, a little redundant here. We have our 1s2, 2s2, 2p6. We already know it's chlorine, tells us that. 3s2, and this is 1, 2, 3, 4, 5. It's 5 high, so this would be 3p5. Okay, now that was pretty easy. It says draw the spectrum that would be produced by sulfur. So look at the periodic table. Chlorine has, so I'm going to write this here, chlorine has 17 electrons. All right, sulfur has 16. So most of it's going to look the same with the exception of the end, okay? Because sulfur is going to be 1s2, 2s2, 2p6, 3s2, 3p4, right? But something else we need to worry about here. Chlorine has 17 electrons, also has 17 protons, right? Well, same with sulfur. 16 electrons, 16 protons. So what do you need to focus on? You need to focus on that number of protons, that nuclear charge. The electrons in chlorine have more of a pull towards that nucleus because you have 17 protons pulling in on those 17 electrons. With sulfur, you only have 16 protons pulling in on those 16 electrons. So it'll be a little bit easier, okay? It'll be easier to remove electrons from sulfur because the nuclear charge is less, all right? They're both in the same energy level. So they're both in level 3 in terms of their valence electrons. So that's kind of a wash there. So ask yourself, if it's easier to remove electrons from sulfur, where will those peaks lie on our readout? Well, where is it easier to remove electrons? It's easier as you move to the right, okay? Because our binding energy looks at 1,000 over here and it's 0 over here. So the first peak for sulfur is still 1s2. You know, it's kind of take a guess here, it'd be about right there. And then sulfur is still going to have a 2s2 and a 2p6. It'll be to the right though, because it's easier to remove those. There's the 2s2, there's the 2p6. The 3s2 will also be further to the right, okay? And the 3p4 will be there as well, but it'll be like this. Okay, so in red, I have the spectrum that would be produced by sulfur. All right, so just something to consider there. If you had to do something like argon, okay, argon would end in 3p6, and everything would be shifted a little bit to the left, right? Because argon has 18 protons, more nuclear charge pulling those in. Okay, next one. Label a sublevel of each peak, identify the element, and draw the spectrum that would be produced by silicon. So let's go through and do this. 1s2, 2s2, see how easy this is after a while, 2p6, and this is half of the s peak, so that is 3s1. Okay, 3s1, that is sodium. All right, so we did number 1. Number 2, draw the spectrum for silicon. So sodium has 11 protons and obviously 11 electrons. Silicon has 14 protons and obviously 14 electrons. Okay, so silicon is going to end in 3p2. Okay, so let's draw this. 14 protons versus 11, so everything is going to be shifted to the left, right? Because to the left on our readout, it's more difficult to remove. So silicon will have definitely a 1s2 peak. It will have a 2s2. It will have a 2p6. Okay. It'll have a 3s2. So we're going to shift that here. 3s2. And a 3p2 right there. Okay. Same height because there's 2 electrons in it. 1s2, 2s2, 2p6, 3s2, 3p2. Okay, make sure you don't get these mixed up with the sodium spectra I had drawn in. These get a little bit more difficult when you analyze them with some of the peaks here at the end when you introduce the D block. You just have to try to think it through, okay? So you want to think about what you have here for like your typical order of filling, right? And then like don't just blindly go 1s2, 2s2, 2p6 all the way to the end, because sometimes things differ a little bit. Some of your practice problems have that. You really got to think about it and pay attention to some detail with what those peaks look like and what the heights are and what you know the electron configuration to be. All right, last one. Label the sublevel of each peak. You know it's oxygen. Draw nitrogen, and then write the ground state electron configuration for oxygen, which we'll do when we do this. Pause the video and give this one a try, and then we'll go from there. Okay, so start with 1s2 for oxygen. Okay, you know, labeling the sublevel, this is our S sublevel. This is interesting though. So I told you guys about before earlier in the video. This is a relative number of electrons. You're going to say, well, this is 4 lines high. So why isn't it 1s4? Well, that's just to give you the scale here. Okay, you really don't need the lines there at all. okay, if you go back a couple slides on the real readout, here it is, you don't have any lines there. You could kind of measure it yourself. I mean, the intensity is over here, right? Well, the intensity of this is like 36. So it's not 36 electrons in that peak, right? It's all relative. So you go here. So you know that 1s2 peak, it's 4 lines high. So your 2s2 is 4 lines high. Now look at the next one. It's 1, 2, 3, 4, 5, 6, 7, 8. It's 8 lines high. It's not 8 electrons, right? Well, what is it? Well, it's twice the peak height of the 2s2. So that has to be 2p4, right? And that's what oxygen does end in. It does end in 2p4. So just take note of that. The peak height here is double what we have here. Makes sense. Draw the spectrum that would be produced by nitrogen. So same as before here, oxygen has 8 protons, 8 electrons. Nitrogen is going to have 7. Okay, will the peaks for nitrogen be further to the right or to the left of the oxygen peaks? Well, with 7 protons, easier to remove electrons from nitrogen. Easier means a less binding energy, less ionization energy, so we're further to the right. So nitrogen will be 1s2, 2s2, and 2p3. Okay, so we're going to go to about, let's see, or about right here, I guess. So that's going to be our peak for that. All right, 2, 3, 4. All right, so that's our last peak there. So that's our nitrogen in red up here. So we have 1s2, 2s2, 2p3. All shifted to the right, a little bit easier to remove. Right, the ground state electron configuration for oxygen, I already have it up here. It's 1s2, 2s2, 2p4. Okay, we know that based on our PES readout. Okay, guys. If you have your practice problems, there's a bunch of them that you can work on after that. Don't get discouraged by some of those. They get a little more difficult, and you really have to, like I said, pay attention to detail and analyze what's going on. This is really neat. It shows you a lot of the inner workings of the subshell theory, our quantum mechanical model, and this is this is the data that we look at, that we use to come up with that. So it's just an extension of atomic theory, and on the AP test in the course, you're expected to know how to read these, tell the element, maybe draw some peaks in, analyze them, and do a lot of the same things here. So hope you guys understood this, and we'll move on from here in a later video. All right, thanks a lot.